Alright, so it's occurred to me that I haven't recorded one of these videos for you guys yet this year. This is a thing that I'll probably do a couple of other times this semester, which is record a video when I know I'm going to be out or when I know a lot of you are going to be out of something that you can kind of work on your own. I did not think to bring my external mic with me, so you're going to have to kind of deal with me sounding a little weird. I went ahead and wrote some stuff on here that we will need to be able to work these problems. These are Coulomb's law calculations, so it's kind of obvious that we're going to need to use Coulomb's law, which is this equation. It says that the electrical force between two charges is equal to the constant K times the size of one charge times the size of the second charge divided by the distance between the two squared. The constant K is the number 9 times 10 to the ninth. You do not need to memorize that, you just have to remember to use it. And remember that weird letter Q stands for charge, and it's measured in coulombs. So let's just kind of dive right into this. The first problem, what is the electrical force experienced by two negative charges of negative 3.5 times 10 to the 6th coulombs that are located 0.45 meters apart? So, the information they've given us in the problem, Q1 is negative 3.5 times 10 to the negative 6th. Q2 is also negative 3.5 times 10 to the negative 6th. The distance is 0.45, and we are looking for the force. So we just have to kind of plug things in to Coulomb's law. FEL is going to be equal to 9 times 10 to the 9 times negative 3.5 times 10 to the negative 6 times negative 3.5 times 10 to the negative 6. All that is over 0.45 squared. So if you plug this whole top line into your calculator, and please make sure you are careful with parentheses and with entering your exponents here, because especially on some of these down a little further where we have to divide by exponents, that is where calculators get so angry. So if you multiply this entire numerator, you get 0.11025 divided by 0.45 squared is 0.2025, and all of that comes out to 0.54. It is in newtons because it's a force. You can't see my answer there. It's actually 0.54444444, but 0.54 is plenty good for us. Alright. Next we have a positive charge. Is located 1.3 meters. Well, a positive charge of 2.8 times 10 to the negative 5th is located 1.3 meters from the negative charge of, oh, let me stop myself for a second. This is a positive number, which actually means that this is a repulsive force. We talked about that at the beginning. It doesn't make a whole lot of sense until you actually think about it, that a negative times a negative, which is going to repel, is going to give you a positive. A positive times a positive, which will repel, will give you a positive. Whereas this next one we'll look at is different. So, I'm just going to write these things down as I go instead of reading and then writing. We have a positive charge of 2.8 times 10 to the negative 5th. You'll notice all of these charges are really small. That's because, like I told you with is actually really large. We invented the unit before we knew what we were dealing with. So 1 coulomb of charge is a huge amount. So Q1 is 2.3 times 10 to the negative fifth. Our distance is 1.3 meters. Q2 is a negative charge of 7.4 times 10 to the negative fourth. And we're again looking for the force. So the math is going to be similar to this one up here. However, our forces or our charges are a good bit bigger. Instead of times 10 to the negative 6, we have one that's times 10 to the negative 5th and one that's times 10 to the negative 4th. So our force here should end up being significantly bigger, even though they are further away. Let's see if that ends up being true. So 9 times 10 to the ninth times 2.3 times 10 to the negative fifth times negative 7.4 times 10 to the negative 4. Again, be careful, so many exponents. All of this is over 1.3 squared. I'm going to pause while I put this in my calculator. Alright, so for that whole numerator bit, I got negative 153.18. And then I immediately did something wrong in my calculator. Turns out problems work better if you write down the numbers right, so it was actually 2.8 times 10 to the negative fifth. So this whole number here is wrong. Instead, it should be negative 186.48. And then we divide by 1.3 squared. 1.3 squared is 1.69, which gives us a final answer of negative 110.34 newtons. The fact that this is negative, strangely enough, means that it's attractive. Again, because we have a negative and a positive, those are going to attract, so even though it may not make the most sense, that means it's an attractive force. Alright, number 3. Two identical charges of 8.1 times 10 to the negative 6th experience a force of 7.5 newtons. How far apart are they from each other? Alright, so we have to switch things up a little here. Our charges are identical, which is like number 1. So Q1 is 8.1 times 10 to the negative 6th. Q2 is 8.1 times 10 to the negative 6th. The force is 7.5 newtons. And we are looking for the distance. Alright, since we are honors level students, we can figure out something about I was going somewhere with that. Oh. Wow, okay. Sorry guys. It's almost like being in class. Since we are honors level students, and the fact that these numbers and these numbers up here are somewhat similar, we should be able to figure out what kind of number our force should be. So these are the same order of magnitude, but 8.1 times 10 to the negative 6 is smaller than 3.5. No, I'm done. That's why I got confused about before. It's bigger. Yes, correct. Bigger. These two numbers are bigger, ignoring the fact that they're positive versus negative, because again, here that doesn't actually mean less than 0. It just means whether we're talking about a proton or an electron. So these numbers are bigger, but they're not that much bigger. They're just a little bit bigger, and yet their force is way bigger than the force from problem 1. So that means that if the force is bigger and the charges aren't that much bigger, then the distance must be smaller. They must be closer together to be creating that extra force. So let's see if we're right about that. Alright, so instead of setting it up like the others, it's going to look like this. It's going to be 7.5 equals 9 times 10 to the 9th times 8.1 times 10 to the negative 6th. Now, we have a choice here. You can write this out again the same way we did up here. Or, since they're identical, you can just do squared. It saves me some writing, and I am lazy student, so I'm going to do it that way. If it confuses you, it is exactly the same as writing it out again. When you're looking for the distance, and it is squared, and it is in the numerator. Now, we need to get distance by itself, and we need to get distance in the numerator. So to do that, I'm going to cross multiply. And when you cross multiply, you end up with d squared over here and 7.5 over there. You could do that in 2 steps. You could multiply both sides by d squared, and then you could divide both sides by 7.5. It's simpler in my mind to think about it as cross multiplication. But whatever makes it simpler for you. So, d squared equals, I'm going to go ahead and multiply this numerator together. So, let's see, that's going to be 9 times 10 to the 9th times 8.1 times 10 to the negative 6th and see, I messed it up because I'm using an annoyingly old graphing or scientific calculator, and so trying to square that piece is a little squirrely. You need to make sure you are squaring the 8.1 as well as squaring the times 10 to the negative 6th. This is why parentheses and using that EE button, if you have one, are so important. I do not have an EE button, and I am suffering for it. This is what happens when you forget to take your calculator with you and decide you want to record a video. Alright, so second attempt at plugging that in, I am getting 0.59 divided by 7.5, because that was just the numerator that I plugged into the calculator. So divided by 7.5 gives me 0.078. That is not my final answer because we don't want d squared. We want just d. So we'll take the square root of both sides. I think I must have plugged something in wrong again. Let me go back and look at my numbers. Nope, I didn't do anything wrong. I'm just a mess. What a surprise. Okay, so you take the square root of 0.078, and you get that your distance is 0.28 that is, in fact, closer together than the 0.45 meters that these two were up here. It may not seem like a very big difference between 28 centimeters and 45 centimeters, but remember that the distance is squared, so distance matters a lot. That's why the force is so much larger. Alright, number 4. Almost halfway there. A negative charge of 6 times 10 to the negative 6 exerts an attractive force of 65 newtons on a second charge that is 0.05 meters away. What is the magnitude of the second charge? Oh, sorry, that was an awkwardly long pause as I thought about things. So, again, we are plugging things back into that equation from the very top. So we have 65 equals 9 times 10 to the 9th times negative 6 times 10 to the negative 6 times Q2, which is what we're looking for. That's what I forgot to write over there. And then all that is divided by the distance, 0.05 squared. Two things. One, this is probably, in my opinion, the trickiest algebra involved in any of these, and you just have to kind of think through it step by step. Two, there's kind of a trick here. It tells you that it's an attractive force of 65 newtons. What kind of charge or what kind of sign do attractive forces have? Why, that's right, student, it's not here with me. Those have a negative charge, so even though it just said 65, the fact that it's attractive means that that's a negative number, which is good, because if we had worked that with that as a positive number, it would give us Q2 as a negative number, and a negative can't attract, and something would be amiss. Alright, so here's what I'm going to do for the sake of space. Hopefully this won't confuse anybody too badly. I am still going to cross multiply. I am going to multiply 6.5 times 0.05 squared. That's going to be 65 times 0.5 squared. So that gives me negative 0.1625. Then I'm going to multiply those two numbers, which is 6 times 10 to the negative 6 times 9 times 10 to the positive 9th. And I am getting negative 54,000. So if I divide both sides, by negative 54,000, the negatives will go away, which is definitely what we wanted. And we did the Q2 is positive 3 times 10 to the negative 6 coulombs. Yay! A force of negative 4.4 times 10 to the third exists between a positive charge, wait, I wanted to write things down as I went. So, a force of negative 4.4 times 10 to the third exists between a positive charge, Q1, which is 8 times 10 to the fourth, and a negative charge, 15 times 10 to the negative 4. What distance separates them? Alright, so let's do some math. This is going to be very similar mathematically to number 3, which means there's going to be that weird cross-multiplying step. To me, it's easier to understand than the kind of squirreliness that happened to number 4. But I don't know if that's true for everybody. Negative 4.4 times 10 to the third equals 9 times 10 to the ninth times, this time they're not identical, so I can't just square it. I have to actually write out everything. My favorite. Again, I'm going to kind of flip these so that I have d squared equals something over negative 4.4 times 10 to the third. That whole numerator. Let me. Alright, so I got, and I plugged that in, I got negative 2,160 divided by 4.4 times, so that's positive, 10 to the positive third. Sorry, I'm super struggling for the lack of a real calculator. So I have that d squared is equal to, when I divided these out, I got positive 0.49. Oh no, that doesn't match the answer. That's because I'm not done yet. I don't care about d squared. I care about d. So I take the square root and get 7.70 meters. Alright, let's look at these down at the bottom. I was mean and didn't give you the answers to these to look at during class, which means I'm not going to know if I'm doing them right, so that's a little scary for everyone involved. Alright, so I have decided that for your sanity and mine, I'm not going to try to work all of these down here that I don't know for sure that I have the right answers to, since I am using my really pathetic calculator. So again, I am not going to work these, but I am going to work the law of ones problems, because you can never get enough practice on law of ones problems. And those I don't need a calculator to do, so it shouldn't be a problem. Alright. Part A. How does FEL change if one of the charges triples? So remember, the way you do this is you plug into the equation, leaving everything the same except what's changing, or plugging in a 1 for everything except what's changing. K will always be a 1, it's a constant. One of our charges is tripled, so it's a 3. The other is staying the same. The distance is staying the same, but it's squared. So the answer that you write on your sheet is 3. The way to talk about that in words is the forest triples. How does FEL if one charge doubles and the other is halved? Okay. So again, K is 1. One of our charges doubles, so it's a 2. The other charge halves, so it's a 1/2. The distance isn't changing, so it's a 1. 2 times 1/2 is 1. So the force doesn't change. C. How does the electrical force change if the distance triples? So, a whole numerator is 1s because nothing up there is changing. The distance is tripling, but the distance is also squared. So 1/9 or 1/9 as much, 9 times less, whatever makes the most sense to you. How does the force change if one of the charges triples and the distance doubles? K is 1, one of our charges is a 3, the other charge is a 1, the distance doubles but is squared. So it's 3/4 as much, or it's 75% as much, whatever. Then last, how does the force change if the distance is halved and both charges double? Okay, so K is still 1, but both charges have doubled, so 2 and 2. The distance is halved, so it's 1/2 squared. So what you end up with is 2 times 2 is 4, 4 over 1/4. Please don't tell me this is 1. 4 over 1/4 is 16. Either plug it into the calculator or think about the fact that it's actually the same as 4 divided by 1/4, which is the same as 4 times 4 over 1. So it is in fact 16 times larger.